let's look at simple mathematical integration.
Okay. So Gerald, you'd asked me to try and integrate this equation earlier, right?
It's the equation that comes from the materials where we have a certain bacterial density model, and if there's a growing area in a circular way, you would have to look to the materials to actually find out how this is derived. But the end of the story is that you get an equation, a sort of quadratic equation, and we'll have a look before we start. And the idea is that we'll find out the number of bacteria in this area if we can integrate. So find out the area that's defined by this function.
Okay, so we want to integrate this with respect to r, is that correct?
R, let's see what is R. R is the radius of our circle, and the function has some, of course, that comes from the area within that circle. And so we have 2 pi, which is the circumference, times r, and then we multiply times this expression in the round parentheses here. And if the radius is growing, then the interesting thing to know would be, how does the area depend on this radius? So yes, the answer is let's integrate with respect to r.
Okay. So the way we're going to do this is we need to tell MATLAB that we are dealing with a mathematical formula. So whereas before, when we've set variables, say the variable r, we've given it a value, 1, 2, 3. We actually don't want to give it a value. We just want to say that it's a symbolic value r.
Just a second, you will have to show your screen.
Oh, okay. Sorry about that. So we weren't showing the screen previously. This is the function we're interested in, the density function. And this is the component that describes the circumference of the circle, and this is the factor that modifies that. So we want to take the integral of this equation with respect to r. So the first thing we need to do is we need to define some symbolic variables. Well, just one. And the way we do that is with this command, syms, sims, and r. So we're telling MATLAB, when we say r in a minute, what we don't want to do is actually have a value for that r, but we should treat that as a symbolic value that maintains its r-ness. So now we can define the function. I'm going to call this nsim. And I'm just going to copy this from above, but turn into the MATLAB syntax. So 2 times pi, MATLAB knows what pi is, times r times 0.1 plus 0.002 times r. That's the same as before. Okay. So this is our symbolic function. And we know it's a symbolic function because it contains a symbolic variable. And finally, we want to integrate this function. I'm going to call this gsim, and this is as easy as using the int function in MATLAB, giving it the symbolic function and telling it which variable to integrate with respect to r. Should we try running this?
Okay.
Okay, it's just warming up a little bit. Okay, so we get a solution. gsim is pi times r squared times r plus 75 all over 750. I guess that's right.
Okay, that's now the way we get the integral in a form that is another function, right? So for one function, the integral is indefinite now. It's not specified over any areas, and we don't get numbers, but we get another function. And as we can see, it's a function still in r. Pi is just a constant, so r is our only variable in that function. And what we can see that we have now, rather than r times r that we had before, now we have r squared times r. So overall, we can see if we look for the highest exponent, r will be a cubic function, or this function will be cubic in R.
Which is from here, the r squared times r.
R squared is multiplied with R, so we have R to the power of 3. Okay, so this is now the indefinite integral, it's a function. What if we wanted to plot that function as we did before? Do we run into any problems?
I guess so. I mean, if we just try plot gsim, I think that's going to cause an error. Yep, that's not possible.
Right, now we have this function, it's called gsim, and we can't plot it. What do we do? First, we have to identify, of course, why is it not possible to plot this function?
So this is a symbolic function, but this isn't actually a MATLAB function in the same way that we've been defining functions previously, either in their own file or as an anonymous function with that @ symbol. So MATLAB doesn't really know what to do with this, apart from do symbolic manipulation.
Right, so we have to get rid of this symbolic character in order to get something that is more algebraic, where we know how to deal with it, using, for example, fplot or, as you said, the function definition. So how can we do this? We can, of course, set it up independently, right? We could just set up our algebraic function as we used with the @ symbol, but let's try a conversion. How can we get this symbolic function to be algebraic directly?
Okay, there was a function called MATLAB function, which is very handy. So I think what would be nice to do is plot the original function, the nsim, and the gsim on the same figure. So I'm just going to do a bit of playing around here, changing our script that we wrote previously. So the first thing I'm going to do is I'm going to change nsim to a MATLAB algebraic function. I'm going to call this nmat. And then I'm going to use this MATLAB function.
So the important thing here is the upper and lowercase way of writing it. Note that the m is lowercase, but there's an uppercase function, f.
And that's called camel case.
Camel case.
If there's a capital letter in the middle that indicates a new word. So this MATLAB function is now going to convert this symbolic function into a function that MATLAB understands. Okay, and we can do the same thing with the gsim. Gmat, gsim. And this will give us a MATLAB function equivalent to this integrated form of the equation.
Right, so we would have a MATLAB function for the non-integrated original function and a MATLAB function for the integrated. The Gmat is the integrated. So we have the original function and its integral, first indefinitely, but we will know then how to use it.
Okay, and now we can do some plotting. Just going to give some space on the screen. Okay, so let's make a new figure. And then we want to add some subplots to this because I want to plot both functions, one above the other. So subplot will give us a 2 rows.
2 by 1, yeah.
And we want
rows,
the
1 column.
First plot. Okay, and then we can use the fplot function to plot a function, because the variable that we have is the function we have is now in the form of a MATLAB function, so we can use fplot. So the unintegrated, the original function was called nmat, and we need to give this limits. As you can see, MATLAB has given us a hint. We need limits. Should we say 0 to 500?
Somewhere, yeah. It's more or less arbitrary, but you have to look into the materials what exactly is needed. But this is now between some limits 0, and if you remember, the limits refers to the r, to the radius. So that's basically a circle is a dot, just no radius, and then up to a radius of 500.
Okay, and also, of course, plotting the other function, 2, 1, 2.
And the second plot goes.
That was called Gmat, and again we want to plot with the same limits.
We definitely want to see that in the same limits.
Okay, So should we see what happens now? Of course, we could add axes and titles to these, but I won't worry for now. But if, of course, you're doing your own scripts, it's always good to specify what the axes and plots are called.
So executing this code produces the figure with two subplots. So remind us, what was the top one?
So the top one was the original function.
Top one is the original function, and the bottom one is the integrated function then accordingly. Exactly. So what do we see? Don't they look very similar?
They do. They seem to have the same, almost the same curve. Almost the same curve. Actually, if you look at the y-axis, then you can see that this is order of magnitude higher than the integrated form is order of magnitude higher than the original function.
Okay, so looking at the y-axis or at the vertical axis, we can see that the integral is much larger. Of course, the area grows much faster than the circumference or the radius. And so what we could do, we could actually try to change the scale and give the same y value for the first plot. So then they would be on the same scale. And if we do this, you can see that now they are no longer the same. The original function basically disappears compared to this cubic function. Of course, the cubic function grows much faster. Another way of learning these properties of functions with exponents. And you know that if you interpret this from the integral, you can, for example, estimate how many bacteria are if they are homogeneously distributed in that area.
Of course, the other way of plotting these two pieces of data, because this is not very easy to see, is plotting them on a log scale. So if we change both to a log scale, then we can see how the, oh, it's lost its maximum. Hold on a second. Okay, you can see how they vary on the log scales as well.
Right. Can you again show us where this log scale is for those who don't know it? Here at the bottom of this graphical user interface where it says Y scale. If you click on that, you get the option to choose between the linear one, which is the default, which we had before, but you can directly convert this into a log scale interactively, very easy.
Yeah, and now you can directly compare two things that have different orders of magnitude. But you can see this is still higher. This is still larger at the certainly at 500 than the original function.
Yeah, of course, because it has to be. Right, so that was integrating the indefinite integral, and we found out how to do it symbolically and how, by using this conversion MATLAB function, how to actually create something that we can plot and look at it as we've been using it with other functions before. So let's now go to the point of finding out values of integrals. How do we get numerical values for specific radii or for specific regions?
Okay, so what would we like? Maybe the integral between 0 and 500?
For example, let's say we have a radius that is between 0 and 500. If we want to find out what is the actual area numerically, so how do we do that?
Well, there's two ways to do this that I know of. So the first way is to do this using our GMAP function, which, if you remember, was the form that we got by using the integral int function on the original algebraic function. So we could just ask what the value of that is at time 500 and subtract away the value of that at time 0.
Right, that's how you do integration between the definite integral between two values. If you have 0 and 500, you take the difference of the function value at these points that you are interested in.
Okay.
And you calculate it by taking the value of that function at 500 minus the value at 0.
Shall I try that?
That didn't work.
I've forgotten a apostrophe.
That's simple colons, yes, for a comment.
Okay, I'm just going to clear the screen so we can see what's going on. Okay.
And now we have this comment in the top, integral between 0 and 500. And because you didn't put a semicolon at the end of this line where the difference is calculated, we get the answer directly in the command window. And it says 6.0214 times 10 to the power of 5. So that's our numerical value. And of course, it's easy to know, it's easy to find out. But remember, you have to use the algebraic version of our integral.
Okay, there is a second method, which I'm going to call the direct method. So recall that we had nsim as our original algebraic function. Well, actually, when we want to translate that when we want to integrate that, we can give more arguments to this int function.
What arguments can you choose?
Okay, so if we try integrating it again, int nsim, we want to integrate with respect to r again, and now if we give it the limits 0 and 500, we should get the same answer.
So there's a bit of a trouble here. So you can work on the symbolic function nsim. You did the integration, and rather than having it indefinitely expressed as a function of r, you now get something that's independent of r, namely in these limits that you've chosen, but you get a formula rather than the number. So we could guess it's the same, or we could use the pocket calculator to find out whether it's the same. Probably MATLAB can do that as well.
Or there is another way, of course. So if I just give this a name for the moment, say sol, and then we use the eval function on this.
Solve for solution.
And then use
what is eval?
Evaluate.
Evaluate, right. So if you have some formula, in this case sol, the solution in terms of a formula, evaluate will give you a numerical answer, just the number rather than this formula where you have to multiply something with pi and divide by 3. So let's run this piece of code and see what it gives us. And if we check this answer, of course, numerically now it's the same as the one that we got previously from the algebraic way. So we had an indirect method where we went via conversion to the algebraic function, and we have the direct method with these optional arguments in the int function for the symbolic function.